The first speaker is Shinsei Ryu, and here is the title. Go ahead.
Okay, thank you. So good morning, everybody. So I'd like to thank organizers for inviting me to come here and to speak about Anderson localization and topological phases of matter. So. Okay. So title of my talk is Topological Phases of Matter and the Anderson localization and actually Anderson delocalization, and also a anomalous or maybe topological transport law. Okay, so it's a work done with Kentaro Nomura in Tohoku University and the Akira Furusaki Riken and the Naoto Nagaosa Tokyo University. Okay, so this is the plan of my talk. The talk is organized in terms of a increasing complexity. So I will start with really the simplest topological phases of matter, which is the quantum Hall effect. And I will move on to the more recent topological phases, a quantum spin Hall effect and the topological insulators. And in particular, my goal today is the transport law in topological superconductors. So I start from 2D with electron system, and going into higher dimensions as well as system without electromagnetic U1 symmetries. Okay. So this part can be thought of as an outline or overview of topological phases of matter and the Anderson localization. So what are topological phases and what the connection to Anderson localization? So topological phases of matter and the Anderson localizations are both big research field and they can be discussed separately. However, it turns out there's a very close connection, and discussing them together is really cross-fertilizing. Okay. So first of all, what is topological phases? So topological phases of matter in condensed matter is something very, very quantum. It's a phase, basically a phase, which has no classical analog. Okay. Okay. There may be a classical Hall effect. However, quantized Hall effect does not happen in classical system. Okay. So I will be interested in a state with a spectral gap. So like an insulator or Mott insulator, there's no low-lying excitations in low energy part of the energy spectrum. There's a big gap. So that is basically my assumption throughout my talk. So what do I mean a topological phases? Okay. So basically, as I said, it's a very quantum state of matter. But what do I mean by topology? Okay. So here, I always have this picture in mind. Okay. So by topological phase, I mean the phase which is distinct from a trivial state of matter. So trivial state of matter, in my mind, it's a state with basically no quantum entanglement. Okay. So like a system which is insulating, but you can think of a trivially insulating state, like isolated atoms which are disconnected. There's no hopping between atoms. It's not conducting, but it's a very boring type of state. Okay. There's no entanglement between different sites or different atoms. Topological phases are insulators. However, it's highly entangled kind of insulator. Okay. So as a consequence, it is not possible to connect topologically trivial state, such as atomic state, and the topologically non-trivial state. So this is a phase diagram, very broad brush phase diagram. So this is supposed to represent a space of all systems with a spectral gap. And let's say, for the sake of argument, consider quantum Hall effect. Okay. So this space is separated by quantum phase transitions, and within each box, we have many states with a spectral gap. So to go from topologically trivial state, which has zero Hall conductance, to topologically non-trivial state with non-zero sigma xy, we have to go through the quantum phase transition. So topologically, there is a topological distinction between states in a sense that it is not possible to connect a topological trivial state and a topologically non-trivial state. So there's distinction of a state of a spectral gap. Okay, so now what is the connection to Anderson localization? So for the topological phases of matter that I speak about today, they typically, or they always have a states which appears at the boundary of topological system. Okay, so topological phases has a spectral gap in the bulk. If there's no boundary, there's no excitations. However, if you make a boundary, there are states appear at the boundary, just like edge state of quantum Hall effect. That is a manifestation of the quantum entanglement. Okay, if they are disconnected atoms, if you cut it somewhere, you don't see anything. However, if there is quantum entanglement between different sites, cutting the system or making a boundary to the system has a non-trivial effect. Okay, edge state in quantum Hall effect is a very special state. It is responsible for the quantum Hall effect, basically. So the focus of my talk will be the effect of disorder on the states appearing at the boundary of topological phases. Okay. Because of the edge state physics, topological state of matter basically offers a very interesting arena of study to the physics of Anderson localization physics. Okay. At the same time, because of very close connection between the states at the boundary and the topological property of the bulk, which we usually call bulk boundary correspondence, studying the edge state of the topological system reveals the non-trivial properties of topological phase. So it works both ways. So studying, topological phases of matter offers an interesting playground for the Anderson localization physics, and at the same time, Anderson localization physics can be basically used to study the properties of topological phases. Okay. So all this just a word. So I want to move on to the examples. Okay. So as I said, I will start from something very familiar to us, and I will increase basically dimensions and also the complexity of the system. Okay, let me first start with quantum Hall effect, which is a state with a spectral gap because of a Landau quantization. And we see all these non-trivial steps or plateaus in transport. Okay, so because of quantum Hall physics, system is characterized not by a one parameter, which is sigma xx, but it is basically characterized by two parameters, sigma xx and sigma xy. So as we all know, quantization of sigma xy has a topological origin. Okay, so in the bulk, sigma xy, which is given in terms of Kubo formula, but you can rewrite it as a integral over some topological quantity, which is guaranteed to be quantized for the system with a spectral gap. So that is basically the secret of the quantization of sigma xy. However, you can also understand the quantization of sigma xy in terms of the physics at the boundary. Okay, so if we have a boundary in the quantum Hall system, these are states in the bulk, which I described as a Landau levels in the previous slide. Here I have a little bit of width, imagining there's some perturbations to the system. But anyway, if I make a boundary to the system, there are states appearing in the middle of the bulk gap. Okay, so that's the edge state. So this state in the spectrum is completely localized on the boundary. Okay. So in terms of edge physics, the quantization of sigma xy simply means that we have a a fully directional states at the boundary, and you can basically count the number of edge mode. Okay, so here it's just 1, but if a sigma xy is, let's say, n, you have a n fully directional or chiral modes propagating at the boundary, which is responsible for sigma xy. So in terms of edge physics, it's just counting. If you have n modes, you have a sigma xy which is n. Okay. Since it is fully directional, as described by this arrow here, there's no backscattering. Okay. That means there's no way to localize the edge state of quantum Hall effect as far as the bulk sigma xy is well defined. Okay. For the later purpose, let me discuss this issue a little bit more. Okay. So that is the something we call spectral flow argument or Laflin's thought experiment. So it really shows why it's not possible to localize the edge state of the quantum Hall system, and at the same time it shows a very close connection between edge state and the bulk topology. Okay, so let's consider a cylindrical system of the quantum Hall effect. So we have a bulk system which is gapped, and I have an edge which is here and here. There are 2 edges. All right, I have a carved up the sample in let's say y direction, and this is x direction. So now I thread a flux. Okay, so this is a magnetic flux, and we will basically study the response of the system to the adiabatic change of this flux. Okay. So since it's a flux, there's a periodicity. So when we change the flux by integer amount in the unit of flux quantum, which is this phi naught, the Hamiltonian or system must go back to itself. Okay. So this is basically when we have n unit of phi, it's indistinguishable from the original system because of the gauge transformation you can make. Okay. So one would think that I will just go back to the original state. Nothing non-trivial happened. Okay. However, it is actually not true. All right. What will happen is the following. So I increase the flux from, let's say, 0 to phi. 0 to phi naught, or maybe just 2 pi. In that case, because of the quantum Hall physics, n unit of charge, some integer unit of charge must be transported from left to right, or maybe right to left, because of the quantum Hall physics. Okay, so that is actually suggesting that system, if I focus on the one edge artificially, okay, system consists of 2 edges, but if I focus artificially on one edge, it means actually we are losing or gaining charges. Okay, so that's something we call an anomaly. All right. So states is propagating in this direction, but in order for quantum Hall effect to happen, charge must be leaking into the bulk to have non-zero voltage drop. Okay. So in this language, it corresponds to the transport of the charge from this edge to another edge, which is quantized, and that is basically saying that charge, if we artificially focus on one edge, it shouldn't be conserved. Right. So why this suggests that what I said before, meaning the edge state of the topological phase should not be localized in the presence of impurities. I can describe this mechanism in the following way. Okay, so let's again take a look at the theory at the edge. Okay, so I have edge theory. So this is the energy spectrum of the edge theory, which is parameterized by kx, and also flux I'm inserting. Okay, so if I increase the electromagnetic flux, we basically push up these energies from this picture to here. So I'm inserting magnetic flux adiabatically, which changes energy spectrum a little bit. But at the end, when we complete the adiabatic flux, adiabatic process, I have to go back to this original picture. So this picture and this picture, in terms of energy spectrum, they're supposed to be the same. If I have these energy spectrum starting from here to here. Okay. However, this occupied state is actually now pushed up to the above the Fermi energy. So I have basically gained a electric charge at the boundary. Okay. So this is in the edge physics. This is the mechanism that I gained the electric charge, which is strange, of course, because I'm not conserving electric charge. Of course, what happens is that in one of the edge, I'm gaining a charge, but on the opposite edge, the dispersion is in the electric dispersion is in the opposite direction. That means I'm actually losing the state on the other side of the edge. Okay. So because of that, I have a pumping of electric charge. So now look at the conductivity along the edge. Okay. So conductivity is basically current correlation function on the edge. So it seems it's related to the second derivative of energy as a function of phi. So you can think of this as a JJ correlation function. Okay. However, in order for the pumping process that I described to happen, this energy dispersion must run from minus infinity to plus infinity. Otherwise, the adiabatic process I described does not give you pumping. Okay. So this means, actually this suggests that this Saurus conductivity should not be zero identically. Otherwise, if that happens, this electric dispersion is completely flat, and there's nothing pushing from the above to the up. So there's no pumping to happen. Okay. So this is basically, it's not quite as qualitative as we wish, but nevertheless, it suggests that the edge of quantum Hall physics for effect, because of this mechanism, should not be localized. Okay. So that's so much for the quantum Hall effect. And for the rest of my talk, I want to basically discuss to which extent we can extend this physics to the wider class of topological phases, including topological insulators in 2D, 3D, and also system without electromagnetic U1 SKH symmetry. Okay. So now we are here. So I'm now moving on to the description of topological phases beyond quantum Hall effect. Okay. So much for the quantum Hall effect, and there's more recent kind of topological insulators, and so I'm now focusing on something we call symmetry protected topological phases. Okay. So remember what I said in the quantum Hall effect. So we have a space of quantum ground state, and they are basically separated by quantum phase transitions. And to go from system without sigma xy to system with non-zero sigma xy, I have to cross a quantum phase transition. Okay. When I'm basically changing my Hamiltonians to cross the phase transition. It is actually, I haven't specified how I change my Hamiltonians, and actually it makes sense to specify how I change Hamiltonians. So that's actually changes rule of the game a little bit. Okay, so now I will change my Hamiltonian in such a way that the deformation of the Hamiltonian respect some symmetry conditions. Okay, so in quantum Hall effect, basically no symmetry is present. Time-glass symmetry is broken by magnetic field. Which is actually implicit in the quantum Hall effect was I still preserve electromagnetic U1 symmetry. So I conserve charge. I change my Hamiltonians, but within that, there's a topological distinction between quantum ground state. Now I impose some symmetries, for example, time reversal symmetry in the space of available quantum state, and I will try to connect one state, let's say in one sector, to another sector, and try to see if there is a quantum phase transition I have to cross. Okay. Because of the symmetry conditions I imposing now, there might be a new quantum phase transitions that can appear, or there may be a quantum phase transition which cannot exist with in the presence of discrete symmetries. Okay. And what I'm describing here, it doesn't have to be two-dimensional. Okay. So it can be 2D, 3D, 1D. So that is something we haven't really noticed in quantum Hall effect in 2D, but we can go to any dimensions basically. Okay. So since I'm describing arbitrary deformation of the Hamiltonian, I'm just describing the structure of the phase diagram, and we have all kinds of Hamiltonians for a prescribed symmetry. So in this context, random matrix theory gives us a natural language to discuss all kinds of possible Hamiltonians. Okay, so so the symmetries I'm interested in is Arturand-Trumbauer symmetries. Okay, so these are the natural symmetries for fermionic systems. So there are 10 of them, and here I mean this 0 plus 1. It's just a symbol to describe symmetries. So we have 10 symmetry classes of Arturand-Trumbauer. And basically, we can ask for a given symmetry, is there topological phases or not? All right. And so the short answer for this is yes. For any Arturand-Trumbauer symmetry classes, we have a topological distinction or topological phases of matter. So that is the basically symmetry protected for new kinds of topological states. So this includes in particular quantum spin-Hall systems and topological insulators, and these are the systems with time reversal symmetries. Arturand-Trumbauer symmetry classes includes also superconducting systems. So there's also a topological distinction in superconducting systems, which I would call topological superconductors. Okay. So these are basically well, recently people are interested in these topological states of matter. We can do something very systematic to study presence or absence of topological states for a given dimension and for a given Arturand-Trumbauer symmetry class. And the answer is summarized as a table. I will not go into the detail of this each entries, but basically, we've just fixed a dimension, spatial dimension, with fixed symmetry. So presence, absence, or time reversal symmetry, and presence, absence, or particle symmetry. And we ask if there's topological phases of matter exist or not. Okay. So integer quantum Hall effect is in one of these descriptions, and also there's quantum spin Hall effect, which is somewhere here, and topological insulators. Okay, so I will not going to describe all these details, but I will try to convey how Anderson localization physics was relevant to derive such such a topological phases of matter. Okay. So the basic idea is what I described in the quantum Hall effect. It essentially extends to all kinds of topological phases. So topological phases of matter is a gap state of matter. So there's nothing to look at in the bulk. So therefore, it's actually a good idea to look at the physics at the boundary of the system. So it turns out boundary of topological system, including topological insulator and topological superconductor, they always evade Anderson localization. Okay, so it's a very special kind of system in a sense that for a system which is not related to topology, the boundary of topological phases, we can basically always, there's a way to localize it. Okay. However, that's not possible for the boundary of topological phases. So once we realize that, we can actually use we can basically reverse the logic. Okay, so we study, we can look for the system which does not show Anderson localization in the presence of even strong impurities. Okay, but once we find such system, it should be described. It should be describing the physics at the boundary of topological phases. Okay. Okay. So that's the. I think I don't have the time for describing everything, but so that's basically topological insulator and superconductor in the wider context. It's a symmetry protected topological phases, and the Anderson localization physics is a way to essentially discover a topological distinction of a ground state in such system. Okay, so now for each cases we can study such system, but now I will take a particular system. Okay, so that is my main part of my talk. So remember what I said earlier. For quantum Hall effect, we can see very close connection between Anderson delocalization at the boundary, meaning I should not be able to Anderson localize the system's boundary in quantum Hall effect, because otherwise it contradicts with the fact that I have non-zero sigma xy. However, essentially same strategy does not work for topological phases in superconductors because of the lack of electromagnetic U-1 symmetry. There's no magnetic flux. I mean, there's a magnetic flux, but since there is no gauge invariance, relying on magnetic flux doesn't seem to work. So I will describe something different here. So I will skip actually this. So it's a new setting. We are now interested in topological phases with no conserved electromagnetic charge. Okay, so it includes topological superconductor like chiral P-wave superconductor, which is basically a state very similar to quantum Hall effect in the sense that it has chiral edge state. However, everything I described in quantum Hall effect essentially doesn't work. Okay, there's also a three-dimensional version of topological superconductor. So there's to complexity here. It's now living in higher dimensions, and there's no electromagnetic U-1 symmetry. Okay, so what should I do? Answer to this is largely implied by it's known basically. So although there's no transport to look at, since the energy and momentum basically are always conserved, even for the superconductor system, of course, we can rely on thermal transport, which will be capturing localization physics or delocalization physics of quasi-particles in quantum in topological superconductor. So I will try to describe the mechanism analogous to spectral flow in the context of a topological superconductor. Okay, but before doing this, let me first give you the description of chiral edge mode in topological superconductor. So it's a very similar setting. I have a phase which is gapped in the bulk, and I have a boundary or edge for the case of two-dimensional topological phase, which is free directional. Okay. In this case, we have a non-zero thermal Hall conductance kappa xy. If we divide it by t, it has some universal number. Okay, so it's quite analogous to sigma xy. Yes. So in particular, in describing the analogous thing to the spectral flow, I will rederive the thermal analog of Schroeder formula. Okay, so here it's again quantum Hall effect. So this is the formula for the sigma xy known as Schroeder formula. So instead of Kubo formula, we have a thermodynamic relation for a sigma xy. So here it's written as magnetization, which is the derivative with respect to chemical potential. And because of some dynamics, it's essentially equal to the derivative of electron number with respect to applied magnetic field. So B coupled to orbital magnetization, and the electrons number couples to chemical potential. And if I take a derivative, this combination, it will give a sigma xy. Okay. So I will basically derive by using, similar to the spectral flow analysis, I will derive the thermal version of Schroeder formula first in 2 dimensions. Okay. But then we can use a thermal analog of the Schroeder formula to study the transport law in 3-dimensional topological superconductor. But main part will be 2-dimensional topological superconductor. So here's the answer actually. So kappa xy in topological superconductor is written as this in the form similar to the electromagnetic Schroeder formula. So this is the whole thermal Hall conductivity or conductance. It is given as a derivative of angular momentum of the system with respect to temperature. And here it's entropy, which is it's a differential with respect to applied angular velocity, assuming you have a disk of the topological superconductor, so you can apply external angular velocity, like external field. Okay, and this V is a quantity which is dimension of velocity. Okay, it is actually velocity of the edge state. Okay, so it looks quite analogous, and it also has a thermodynamic origin. So angular momentum couples to external velocity, and entropy couples to temperature. Okay. So how I do? So the question is, how do I derive such transport law? But before doing this, let me say this you can measure in 2-dimensional topological superconductor, and the magnitude of the effect depends on this velocity v and also the heat capacity of the system. So you can basically slightly change the applied angular velocity, which will be causing the temperature drop across the samples in this direction. Okay. So now the question is, how do I derive this? And here I will be using the geometrical analog of electromagnetic flux. Okay. So there's various ways to derive this. One in terms of Kubo formula, which is perhaps elementary, but I will take a derivation in terms of edge states physics. Okay. So I will first consider the cylindrical system with 2 edges, and actually I can focus on disk. In that case, there's only 1 edge, and I will write down the partition function of the system. Okay. So given all bulk excitations are completely gapped, it makes sense to write down the partition function in terms of edge physics. Okay. All gapless excitations are living in the boundary. Okay. So this is my partition function in the presence of finite temperature and the finite angular velocity, which couples to the momentum of the boundary. Okay. So this Hamiltonian and this partition function can be rewritten this way, and there's the parameter tau which I introduced here, and the real part is essentially beta times. Sorry, imaginary part is essentially temperature times velocity, and imaginary part, real part is essentially the angular velocity omega z. Okay, so this is just a compact way to write. And in this notation, we immediately notice that these 2 parameters enters in the partition function as a modular parameter. Okay. Essentially, this modular parameter is playing the role of electromagnetic flux in quantum Hall effect. So the derivation I'm describing will carry through for the derivation of electromagnetic state formula if I replace this parameter, modular parameter, by electromagnetic flux, and if I replace Hamiltonian and momentum by electromagnetic current and electromagnetic charge. However, since I don't have electromagnetic charges and the current, conserving a superconducting system, I am just using Hamiltonian and the momentum. And they are they don't couple. They do not couple to applied field, but they will couple to the geometry itself. Okay, so changing this modular parameter adiabatically, we can basically measure the response of the system, which will give us the thermal storage formula. The derivation is very simple. So first we can write down thermal current as a derivative of current flowing down the boundary with respect to temperature. On the other hand, we can also write down entropy. Almost by definition, it's a free energy with derivative with respect to temperature. Okay, so but then we can notice that you can switch the differentiation. So here's a t appearing here, and there's also the angular velocity, the differentiation with respect to applied angular velocity applying here. Okay, you can basically have two differentiations to do, and you can just switch the order of differentiation, and we immediately notice that we can establish this formula. Okay, so derivation is very simple. So I think I'm running out of time now, but let me say for the remaining maybe 3 minutes that we can use the two-dimensional Schrader formula to build the response of three-dimensional topological superconductor. Okay. So again, going back to electromagnetic situation, we have a topological insulator. Okay. So in that case, we have a topological magnetoelectric effect, which is analogous to quantum Hall response, but now it's in 3 dimensions. So it's a 3-dimensional topological insulator is characterized by this response, meaning if you apply electric field, this is now the cylinder of 3-dimensional topological insulator, magnetization, orbital magnetization follows in the same direction. Okay. Similarly, if I apply a magnetic field in the 3-dimensional topological insulator, polarization follows in the same direction. So that is the characteristics of 3-dimensional topological insulator. Now applying the same, applying the 2-dimensional thermal state formula onto the surface of 3-dimensional topological superconductor, we can derive a similar formula for the thermal topological effect. So here I essentially replace electric field by temperature gradient, which is like a driving force for the thermal current. That is this Eg. Okay, that will induce the magnetization and analog of magnetization. That is the angular momentum. Okay, so if you apply temperature gradient to the topological superconductor, sample will rotate adiabatically. Similarly, there's a dual response for that. So if I apply external rotation, if I force the sample to rotate, it will cause a temperature difference to the top and the bottom of the topological superconductor. Okay, but anyway, this is, I don't think I have a time to describe the whole detail. So I'll go to the summary. So in the first part of my talk, I describe the topological state of matter as a system which supports Anderson delocalization at the boundary. And this physics at the boundary reflects the anomalous, reflect as anomalous transport law in the bulk of the topological system. And we derived the thermal transport law for the 3-dimensional as well as 2-dimensional topological superconductor, which is summarized here, and it's completely analogous to the electromagnetic response of 2D and 3-dimensional topological insulators. Okay, thank you very much.
Questions? Comments?
So
Yeah.
is this class C1 or do you
Yes, I didn't specify the class. This corresponds to class D in 2D and class D3 in 3D. And for class C1, we can use spin current. I haven't worked out, but as this
there you have an extra
right, extra conservative.
spin is conserved.
Right.
You can use proper spin.
Right.
Yeah.
Maybe say, so are these characteristics that are shown here sort of quantized,
Yes, so it's
like Hall conductance?
right. So it's not as quantized as Hall conductance because of this velocity. Okay. So it's analogous to central charge in 1+1D conformal field theory. So you try to extract central charge by thermal measurement. You can measure specific heat, but you have to normalize specific heat by velocity to get central charge, which is universal. So, but for the case of Hall conductance, it's always speed of light, so it's easy to normalize. Yes.
Thank you.